Welcome to this physical hydrology course. GO2 4203 Physical Hydrology is a bachelor's level 2 course in Earth Sciences at Utrecht University. Course coordinator is Dr. Michelle van Vliet to my left, and I, myself, Martin Hendricks, I will take you through the lectures. Normally, I lecture for a classroom filled with students, but we're amidst the coronavirus pandemic at the moment, unfortunately, which is the reason why we have changed the course to an online course. Also, the course was shifted from year 2, period 1, to now, which is year 1, period 4. What is essential for you to be successful in the course is that you have the textbook in your possession at the beginning of the course. You find the URL stated here. You can buy the textbook in the bookstore, or you can borrow the book from a student who participated in this course earlier on. I don't care, but I do care that you have the textbook in your possession. This is really essential. First of all, now you have the textbook, is browse through the book, read the section Welcome to the Book, browse through the remaining part of the book. At the end, you find some extra help with mathematics. And at the end of the book, there is also a section which gives you in part answers to the exercises. So this can also come in handy, helpful when you're struggling with these exercises. It's absolutely essential that you struggle with the exercises. The proof of the pudding is in the eating, as the English say, and you learn hydrology by doing, not only by reading or hearing about it, but by sweating over an exercise. That's the way it is. There is also an online resource center, which is sometimes called the companion website, and you'll find it at the Oxford University Press site, and the URL is given here. It gives you heaps of interesting information. The errata, the foutjes, vergissingen of the latest print are documented there. There is a selection of multiple choice questions for the chapters 2 to 5. Also included is feedback to help check your understanding of the key concepts covered in these multiple choice questions. There is a series of interactive spreadsheets related to topics introduced in the book, and there is a library of interesting web links. Also, additional exercises to chapters 1 and 2 are provided in the online resource center. And I have to thank Professor Charles Fitz for this, professor at the University of Southern Maine in the US, who sent these to me. By the way, Professor Fitz is also the author of an excellent textbook that we use in our Master's Earth Sciences program, Earth, Surface and Water. And his textbook is called Groundwater Science. So browse through the textbook and browse through the online resource center. And then for the students at Utrecht University, they also have access to Blackboard. So also browse through Blackboard. You will also find errata to older prints there. So if you have a first printing of the book, then you have a harder job to adjust the book by its errata than when you have the latest print of the book. But you'll find all the information there. If you want to know what imprint, what printing of the book you have, you can look at the copyright page in the book at the beginning, which is the page which is facing the page where it says to Anneke. And on the copyright page, you will find a strange string of numbers at the bottom. And the lowest number listed indicates the imprint, the printing number. So if the lowest number is 1, you have the first printing of the book. But if the lowest number is 8, you have the 8th printing, the 8th imprint of the book. In addition to the people that I thank at the beginning of my book, I would like to thank Professor Hubert Savenije, Emeritus Professor of Hydrology at Delft University of Technology also. He, after scanning through, reading the first print, he came up with some useful remarks, and I used that for later imprints of the book. I would also like to thank a master's student, Wouter Govers, master student of Earth Service and Water program, and I had a useful discussion with him about figure 4.17, and this led to me inserting a new figure 4.70 for the latest printings of my book. What's also important is the course guide. It has been sent to you, but you can also find it at Blackboard. So Michelle van Vliet and we are happy to take you through this course. Michelle has everything set up. We are using Microsoft Teams. She will be assisted by 4 student assistants who made a pretty good job of attending this course earlier on. And as said before, I will take you through the lectures. If you have any questions, ask Michelle or ask me or ask the students, assistants, and then preferably during the during the hours that are allocated for this. So I wish you a lot of success with this course. My talking head will disappear now and only to resurface in chapter 3, part 1, because that's a recording that I did earlier, and also in the answer to some exercises. I wish you a lot of success with this course. This is the textbook. This book is written from a clear didactic concept that I developed over more than 2 decades of teaching hydrology at Utrecht University to both undergraduate and graduate students in physical geography, environmental sciences, and earth sciences. Chapter 1 of the book deals with the hydrological cycle, the hydrologische kringloop, which is the central concept in hydrology. The central unit in hydrology is the drainage basin or catchment, het stroomgebied, and the central equation in hydrology is the water balance, de waterbalansvergelijking. The book will deal with a number of equations which are stated here: the energy equation, the Bernoulli equation, the flow equation, which is Darcy's law, de wet van Darcy, or the Darcy-Buckingham equation, and the continuity equation, the water balance equation. This is chapter 1, the introductory chapter, and other chapters are chapter 2 on atmospheric water, which has a link with meteorology. Chapter 3 is on groundwater. Groundwater is water in the subsurface below the water table. All interstices, all pores are fully filled with water, are fully water saturated. Then chapter 4 will deal with soil water, which is water in the subsurface above the water table, where you have air in the pores also. So you have both air and water in the pores, slightly complicating matters. And then chapter 5 will deal with surface water, and surface water essentially can be turbulent flow, which is more difficult to describe than laminar flow. What's important is that you follow the book's didactic concept, and as already stated earlier, exercises play an essential role. Making the exercises, struggling with the exercises plays an essential role in this. For Chinese students in the course, the book is also available in Chinese using simplified Chinese characters, and you can order the book at China Meteorological Press. Here we have the hydrological cycle, the hydrologische kringloop. This is a picture after Ward and Robinson. their textbook Principles of Hydrology, an excellent textbook, but of a more descriptive nature than my textbook. To the lower right, we see the ocean surface. The ocean surface is heated by the sun, by sun rays. Because of this, the water is heated. The molecules, the water molecules, they start to move more quickly. They get more excited. Because of this, they escape from the ocean into the air above, a process which we call evaporation, verdamping, evaporatie. And also the air above the water is heated, and immediately as a process, this heating, this temperature wants to be distributed over a larger column of air. So we get that the air starts to rise, and also because the heat is distributed over this larger column of air, this rising air starts to cool. So what we get is rising, cooling air above the ocean surface. At a certain height, the air will become fully saturated with water vapor. Why is this? This is because warm air can contain more water vapor molecules than colder air. Well, the air was rising, was cooling, so at a certain height it is fully saturated with water vapor, and if the temperature drops further, then the water vapor will start to condensate. And the level, the height at which this takes place, we can see that because that's the level, the height where we get clouds. Clouds are very small water droplets floating in the air. These water droplets can coalesce, they can grow bigger, get that big that they cannot be held in the air against the updraft of the air, and then they start to fall, a process which we call precipitation, precipitatie, neerslag. And precipitation can be in different forms. It can be snow or hail, or it can be rainfall. Very often in our latitudes, which is in the mid-latitudes, we have that the precipitation starts as snow higher up in the atmosphere and then lower down in the atmosphere because of the higher temperatures change into rainfall. Water falls on vegetation or buildings on the land surface or on the land surface itself. Water can become intercepted by vegetation or by buildings, a process which we call interception storage, so the amount of water per unit of time that is stored on vegetation or buildings, and from there it can also evaporate back into the atmosphere, a process we call interception evaporation. So that's the amount of water per unit of time evaporating from these leaves of trees or from these rooftops of the buildings, etc., back into the atmosphere. Water which falls on the land surface can infiltrate into the land surface, a process we call infiltration, infiltratie. It can move further downward towards the water table and then become part of groundwater flow, or it can also flow above the water table, either as soil water flow or even further upward as overland flow, water flowing over your land surface. I'll come back to these processes later on. Groundwater flow, soil water flow, overland flow all contribute to surface water flow, water which is flowing in your rivers and which is taking the water back to the sea and to the ocean. And in this way, the hydrological cycle is closed. Of course, there are many, many shortcuts to this system. Precipitation, neerslag, falls on the landscape. It may fall on vegetation. The amount of precipitation per unit of time falling onto the top of a vegetation canopy is the gross precipitation, bruto neerslag. The amount of water stored on plant surfaces in a period of time, either as intercepted rain, snow, or ice, is referred to as interception storage, interceptieberging. Precipitation that is intercepted by vegetation or buildings may evaporate back into the atmosphere. This process is called interception evaporation, interceptieverdamping. Evaporation from the stomata, numerous small pores of living leaves of plants, thus from within the plants, is called transpiration, transpiratie. Throughfall, doorval, consists of raindrops that fall through spaces in the vegetation canopy and that drip from wet leaves and branches. Stemflow, stamafvoer, is the process of water running down the main stem of a tree. This can be a large quantity per unit of time, as the precipitation that is captured by leaves and branches in the vegetation canopy is concentrated along the smaller area of the stem. The amount of precipitation per unit of time that reaches the ground surface is the net precipitation, netto neerslag. Net precipitation is made up of the quantities of throughfall and stem flow per unit of time. On contact with the soil, water may trickle into pores or cracks of the soil, a process that is called infiltration, infiltratie. Within the unsaturated zone, the onverzadigde zone, water may move further down to the water table, de grondwaterspiegel, a process known as percolation, percolatie. Finally, evaporation from the soil is simply called soil evaporation, bodemverdamping. This slide is to explain the positioning of the water table in easy terms. If you are able to dig a large pit, the level to which the water from the ground rises in that pit is called the water table. And the water table is in between your unsaturated zone and your saturated zone. This is a picture from my PhD days showing the Kriepsbach catchment in the Goodland in Luxembourg. You can see here the plateau, which is made up of Luxembourg sandstone. Here is the Cuesta rim, and here you're entering into the Kuiper marls. All the precipitation that falls on this area leaves the area at this point as surface water flow. So this is an example of a drainage basin, an example of a catchment, or in Dutch, een stroomgebied. This picture shows us two catchments in cross-section view, a catchment to the left and a catchment to the right. And usually your topographic boundary also gives you your catchment boundary, but as you can see depicted in this picture, there is a permeable layer in the subsurface, so rainfall falling on this area or water moving from upslope can enter into this permeable layer and is discharged into your left catchment, meaning that your catchment boundary is situated here rather than at the topographic boundary. Also, ideally, you would like your catchment to have a sealed surface at the bottom so that there is no leakage of water out of your system, and the only location where water is leaving your system is the outlet point of your catchment. Here we have a generalized scheme of drainage basin processes, of processen in een stroomgebied. In small captions, in kleine letters, we have the processes, for instance, precipitation, volumes of water per unit of time, and in large captions, in hoofdletters, we have the storages over time. Dus zoveel volume water wat geborgen is gedurende een bepaalde tijdsperiode. We have precipitation It is intercepted. The process is called interception. Interception storage on the vegetation, on leaves and branches. From there it can evaporate. We know that process as interception evaporation, or it can drip from the leaves as throughfall, or it can flow along the stem of trees as stem flow, doorval en stamafvoer. Het collects at the land surface. Het verzamelt zich aan het landschapsoppervlak. A process we call surface detention or depression storage. Oppervlakteberging. En van daaruit kan het weer verdampen. From there it can evaporate. But it can also flow over the land, overland flow towards your stream. From the land surface, from the storage at the land surface, it can infiltrate into the subsurface, into your unsaturated zone, your soil water zone, a process called infiltration. It is stored as soil water, and from there it can also evaporate as soil evaporation, bodemverdamping. But it can also flow through your soil matrix, or it can even bypass your matrix. I'll talk about that later on, and contribute to your surface water flow in your stream. It can move further downward from the unsaturated zone into the saturated zone, so from your soil water storage to your groundwater storage, a process which is called percolation. And I will go into detail about this process also later on. From your soil water body, I already said it can move as soil water flow to your surface water, but also from your groundwater body, there can be a slow, sustained flow into your surface water system, which is called groundwater flow. All this water collected here, it's stored in your streams, and it can leave your at the catchment outlet. It can leave the catchment at the catchment outlet, a process we call discharge, in Dutch afvoer of debiet. Of course, from this surface water, it can also evaporate. And then there is a process I did not mention, which is channel precipitation. That simply is the precipitation that is directly falling on your streams, on your surface water. Channel precipitation. And there is the process here of leakage, which in actual fact is the process that I talked of earlier. If your catchment is not sealed at the bottom, you can lose your water to deeper down. So this water is not leaving the catchment at the catchment outlet point. This generalized scheme also shows us that we have input into a drainage basin, precipitation, and we have output from the drainage basin, which is evaporation, leakage, and discharge. And these are all processes, volumes of water per unit of time. But we also have storages within the system, which are given with these rectangles: vegetation, land surface, soil water, groundwater, and surface water. And soil water and groundwater and surface water are also the subjects of the coming chapters 3, 4, and 5. As a water balance, input as a volume per unit of time equals output as a volume of water per unit of time plus change in storage over time. Let's take a closer look at the water balance. And as an example area, we can use the Kriepsbach catchment, the catchment shown here. This is the catchment boundary. Here is the outlet point, and the catchment area is 2.66 square kilometers. Now, the water balance is basically the bookkeeping of the volumes of water per unit of time that is entering the system, inflow, or that is leaving the system as outflow, or that is leading to a change in storage in the system in that same specified period of time. So when your inflow, volume of water per unit of time, is larger than your outflow, volume of water per unit of time, then water is taken into storage in the system over that same period of time. And your change in storage, delta S delta T, is positive. When your outflow, volume of water per unit of time, is larger than your inflow, volume of water per unit of time, then water will be taken out of storage during that specified period of time. And delta S delta T is a negative number, smaller than 0. If you were to look at the system for a hydrological year, for instance, you're looking at averages over that hydrological year, then the storage at the beginning of the hydrological year is the same as the storage at the end of the hydrological year, meaning that roughly there's the same amount of water stored in your unsaturated and saturated zone. So your water table levels may be the same, and your change in storage over the year then is 0. And then this bookkeeping equation simply then becomes inflow is outflow. Now let's look more specifically to the Kriepsbach catchment. The incoming terms, the inflow is your precipitation, and the outgoing terms are your discharge at the outlet point plus your evaporation from the catchment. And then inflow is outflow plus change in storage over that period of time. In the book, I'm giving you the example of the water balance of the Netherlands, and when you're working with the exercises in chapter 1 and also the additional exercises that you find on the online resource center or in Blackboard, then there are some tips I will give you, some rules that you should always abide with. Always use a strictly defined area, or in this instance, drainage basin. You cannot state the rainfall for a certain portion of the catchment and then look at the discharge from all of the catchment and insert these numbers in this equation. That's logical that you don't do that, but also look at the strictly defined period of time. If you're looking at rainfall during a certain day, you must look at the discharge and also the evaporation and also the change in storage over that same day. So in essence, it's always, you're looking always at volumes of water per specified unit of time. Use fixed unit of measurements. You cannot insert precipitation in millimeter per day and, for instance, insert discharge in cubic meter per day. So you must either rework rainfall from millimeter per day to cubic meter per day, or you must transform your discharge from cubic meter per day to millimeter per day. And what lies in between these values in millimeter per day and cubic meter per day, that of course is your catchment area. So if you want to go from millimeter per day to cubic meter per day for your precipitation, multiply by your catchment area. And if you want to go from cubic meter per day to millimeter per day for your discharge, divide by your catchment area. Of course, when you express your discharge in millimeter per day, this by no means is a velocity of your water flow. It simply is a volume of water per unit of time and per catchment area. As a preparation for chapter 2, I would like to ask you to take a look at this short film, which is the opening film of De Wereld Draait Door, which was a popular TV program at 7 o'clock in the evening. Take a good look at this short film, and I'd like to hear your major comment. Also, take a look at the films explaining Coriolis at the equator. There are 2 films. look closely at these films. I would like to hear your observations and comments, and I would like to hear your major conclusion. I would like to ask you to study chapter 1 and prepare for chapter 2 and make the exercises of chapter 1 as are indicated in the course time schedule that was presented to you by Michelle. Study well.